So we have a binomial, and that's simply the fact that it's got two terms in the bracket. If you had three, it'd be a trinomial. And because it's only a power 3, what most of us use is the trusty Pascal Triangle, named after a French mathematician, Blaise Pascal, credited with developing the world's first mechanical calculating device, although there is evidence that the Chinese had exactly the same pattern of numbers some 5,000 years before Pascal. So anyway, if you have got a plus b to the power 3, then the triangle will give you the coefficients, and your first term descends in power and your second term ascends in power, and so this is what you should get. Now I'm just doing it for the sake of completeness. I know that 1a cubed is just a cubed, so therefore you'll get a cubed plus 3a squared b plus 3ab squared plus b cubed, or something equivalent to that. Now there's lots of different ways. So what I've got to do is to do 2 plus y to the power 3. So clearly I'm going to go through, and I've got 2 cubed plus 3 times 2 squared times y, and I don't really need the brackets, but I'm going to put them there just to be sure. 3 times 2 times y squared plus y cubed. Again, I definitely didn't need the bracket there, but now last time I checked, 2 cubed was 8. 3 times 2 squared gives me 12, because 2 squared of course is 4. 3 times 4 is 12. 12y plus 6y squared plus y cubed. There's my binomial expansion. It did say or otherwise, so you could, if you really wanted to, do 2 plus y times 2 plus y, and classic thing there, 4 plus 4y plus y squared, and then multiply that by 2 plus y again. As long as you make sure you distribute everything, you'll get exactly the same thing. So you could do it that way if you wanted to, but most people would go a binomial expansion. So what we had was that our 2 plus y all cubed was 8 plus 12y plus 6y squared plus y cubed, and we're required to show, hence is a good word, truhin. That means use what you've just done. Don't do it by any other way. Use what you've just done. So it's 3 marks. So I've got to show each of my little bits. 2 plus x to the minus 2, all to the power 3. So clearly my 2's the same. In this particular case, that y is equal to x to the minus 2. So therefore this is going to be exactly the same as 8 plus 12x to the minus 2 plus 6x to the minus 2 squared plus x to the minus 2 cubed. Now don't make stupid errors here. Okay, 8 plus 12x to the minus 2 plus 6. X to the minus 2 times x to the minus 2 is x to the minus 4, and what some people do is just multiply the powers together. Okay, which you can do, x to the minus 4 plus x to the minus 6, because it's x to the minus 2 times x to the minus 2 times x to the minus 2, and you add the powers together. So repeated addition of minus 2 3 times is the same as 3 times minus 2, so you multiply the powers together. So remember that x to the a all to the power b is actually x to the a b. Now my other one is 2 minus x to the minus 2 all cubed. So I'm going to get exactly the same coefficients. The only difference is that on my odd powers they're going to be negatives. Minus 12x to the minus 2, because it's a minus x squared, and if you raise it to an odd power like we do in here, those terms will be negative. This would be a plus 6x to the minus 4 minus x to the minus 6. Okay, and those two added together is going to give me 8 times 8, which I think is 16. 12x to the minus 2 minus 12x to the minus 2 disappears. I've got 6x to the minus 4 plus 6x to the minus 4, which is 12x to the minus 4. And x minus 6 minus x to the minus 6 disappears. So what I've got is that 2 plus x to the minus 2 all cubed plus its conjugate. There's an interesting word. Exactly the same terms, just opposite sign in between. So we tend to use conjugates when we're dealing with complex numbers, but that's going to give me 16 plus 12x to the minus 4. So I've expressed it in the required form, and I can push on from there. Okay, so hence again, we've got this again, use what you've just done. So therefore what I've just managed to show is that this bit in here is the same as 16 plus 12x to the minus 4. So instead of doing the whole of that integration, I'm going to just replace that by 16 plus 12x to the minus 4. Technically it should be all bracketed with respect to x, and we know that you can integrate one term at a time, and the way to integrate is to increase the power and divide by the new power. So therefore what we'll get is 16x, because of course that's 16x to the 0. You increase x to the 0 by 1, you get x to the 1, you divide by 1, you get 1. I'm not going to put division by 1, plus 12x to the minus 3 divided by minus 3, and I would be explicit to show that, plus a constant. Now the reason we put a constant in is that integration is the reverse of differentiation. And if you differentiate a constant because it has no gradient, it disappears. When we're integrating, reversing it, there might have been something there that we don't know about. Okay, so I would tidy this up. I wouldn't leave it in that form. Certainly I'd leave 16x minus, so 12 divided by minus 3 is minus 4, so minus 4 either x to the minus 3 or over x cubed. It doesn't make any difference, but don't ever forget your plus c. 2 marks. That's reasonably consistent in terms of the amount of work I have to do. So I've got exactly the same function as I had before, except this time I've got limits, and so they're using this word hence, which means use what you've done before, truhin. So my integration will be exactly the same. The only difference is I've got limits. When I integrated it before, I ended up with something quite nice. 16x minus 4x to the minus 3 plus c, and this time I've got my limits 2 and 1. So essentially I'm going to end, and it's only worth 2 marks, so it should be fairly quick, fairly simple, and obviously I'm writing more here than perhaps I should do, but it'll do. I've got 16 times 2 minus 4 times 2 to the power minus 3 plus c. I've already said I don't really need the c in there, but I'm going to keep it there just to show what happens, minus, then I've got 16 times 1, the lower limit, minus 4 times 1 to the power minus 3 plus c. And you notice I've bracketed my second function. In fact, I've bracketed both of them, and that negative sign must distribute, so I've got to be very careful. So I've got 32 minus 4 times 2 to the minus 3 is 1/8, so 1/8. So that tidies up to give me a half, plus c, minus 16 plus 4 minus c. So my c's will cancel. I've got 32 minus 16, which is 16, plus 4, which is 20, minus a half. So it doesn't really matter how I do this. My first bracket, if some people like to do them in brackets and then minus it, it doesn't really make any difference. So what I've just said is that I've got 32 minus 16, which is 16, plus 4, which gives me 20, minus a half, which gives me 19 and 1/2. But I would personally prefer to write that as 39 over 2.
In this question, the indices rule x to the a to the b equals x to the ab is mentioned, with a brief explanation. Hopefully most of you watching this video will have seen the derivation of the indices rules, but if you haven't, or if you could do with a reminder, then carry on watching. Understanding the derivation of things in maths is interesting itself, but also is a good way of helping you to remember things, particularly when you're under pressure. So, starting with the most basic one, we have x to the power of a times x to the power of b equals x to the power of a plus b. Now, if we just look at this in terms of whole numbers, we can have a look at an example. So, say we had 2 cubed times 2 to the power of 4. Well, that would be 2 times 2 times 2, so we've got 3 of them, times 2 times 2 times 2 times 2, and we've got 4 of them. And so the total number of 2's that we have is 3 plus 4, which tells us that we have 2 to the power of 3 plus 4, or 2 to the power of 7. So that's pretty straightforward. And we get a similar sort of thing happening with subtraction. So, or division leading to subtraction, I should say. So if we have x to the power of a divided by x to the power of b, and that's x to the power of a minus b, well, if we had, say, 3 to the power of 5 divided by 3 squared, that would be 3 times 3 times 3 times 3 times 3. So there's 5 of them on the top, and 3 times 3, 2 of them on the bottom. And then what we do is we can cancel, and if we cancel these ones, we are left with 5, the original 5, take away the 2 that have been removed, cancelled. So that means we have 3 to the power of 5 take away 2, or 3 cubed. Now the next one to consider is that we know that x to the power of 0 is 1. That's if x is not equal to 0. If x is equal to 0, then we have 0 to the power of 0, which is sometimes described as undefined, but sometimes mathematicians decide in particular topics to define 0 to the power of 0 as 1, or sometimes to say that it is undecided or undeciderable. Anyway, we're not too worried about the x equals 0 case, we're just thinking of any other number to the power of 0 being 1. And why should we accept that? Well, one way of doing it is to use what we already do accept. So if we say that, say x to the power of 4 divided by x to the power of 4, well, on the one hand, we would say that that's 1, because it's a number divided by itself. But on the other hand, we can use the rule we've just agreed upon and call it x to the power of 4 take away 4. That is x to the power of 0, and therefore we have x to the power of 0 is 1. Okay, so now we could perhaps have a look at a negative power. So what would x to the power of minus 3 look like, for example? Well, what you've been using for that is 1 over x cubed. So why should that be? So far we haven't really looked at negative numbers, but we can use the methods from above. So we could do an example, or we could say that we have x to the minus 3 equals x to the 0 take away 3, and that equals x to, by the rule above, that equals x to the 0 over x cubed, which is 1 over x cubed. So penultimately we have fractions to look at. So let's say we have x to the power of a quarter, and we would say that's the 4th root of x. So why might this be? Well, using the rules we've looked at so far, we could say x to the power of a quarter times x to the power of a quarter times x to the power of a quarter times x to the power of a quarter is x to the power of a quarter plus a quarter plus a quarter plus a quarter. That is equal to x to the power of 1, which is equal to x. Now, we can also call this thing x to the power of a quarter to the power of 4. So x to the power of a quarter to the power of 4 is equal to x. And if we now take the 4th root of both sides, we have x to the power of a quarter equals the 4th root of x. Now, one thing we didn't actually look at so far is the one that we started with that came from the question. So what we can do with that one is do it in a similar way to the other ones and stick some numbers in. So say we had 7 squared cubed, that would be 7 squared times 7 squared times 7 squared, and from the rule just below, that means we have 7 to the power of 2 plus 2 plus 2, but of course the 2 plus 2 happens because we have 3 lots of 2, and so that establishes that rule. So that would be 7 to the power of 6. Now, going back to our last one that we did before that, the fractional one, we could have just, once we've established that one that we're happy with, we could simply go for x to the quarter to the power of 4 equals x to the quarter times 4 equals x to the 1 equals x. And that then establishes the idea using that last line there.